Hello everyone. Welcome to this course on installation and commissioning of electromechanical equipment. I am Chin Fudi. In this lesson, we will learn the working principle and common applications of stepper drivers and stepper motors. Stepper motors are essential devices for achieving high-precision position control and are widely used in CNC machines, 3D printing, and industrial automation. Next, we will start from the following perspectives. Let's first look at the learning objectives of this lesson. We will focus on learning the basic principle, control methods, and hardware wiring structure of the stepper driver, the dip switch settings, motor wiring methods, and microstepping setting, as well as how to calculate the required pulse count of the PLC. We will also include a hands-on wiring demonstration to help you gain a more intuitive understanding of the working process of a stepper control system. Number 1. Working principle and types of stepper motors. A stepper motor is an actuator that converts electrical pulse signals into angular or linear displacement. It plays a crucial role in open-loop control systems. When the control system sends a pulse signal, the stepper driver converts it into time-division multi-phase currents, which drive the motor to rotate a fixed angle, i.e. a step angle. By sending a series of pulse signals, continuous rotation can be achieved. The control system can adjust the motor's position and speed by varying the number and frequency of pulses. Common types of stepper motors are as follows. 1. Permanent magnet PM type. They are typically two-phase, featuring relatively small torque with step angles of 7.5 degrees or 15 degrees. They have a simple structure, suitable for low-speed and light-load applications. 2. Variable reluctance VR type. They are typically three-phase and capable of producing higher torque. The step angle is as small as 1.5 degrees, but they produce greater vibration and noise. They are gradually phased out in developed countries. 3. Hybrid HB type. This type combines the advantages of both PM and VR types, with a more complex structure and higher precision. The two-phase step angle is 1.8 degrees, while the five-phase step angle can be as fine as 0.72 degrees. This type is most widely used today and considered the mainstream solution. Number 2. Description of functions and interfaces of stepper driver. A stepper driver acts as the control unit that supplies the appropriate current to each phase winding of the stepper motor in a precise timing sequence. Its main role is to ensure accurate control and stable motor operation. Using the M542 stepper driver as an example, its module interfaces are as follows. 1. Interface P1 signal input, pins 1/2. Pulse signal, connected to Q0.3 and 0V. They control motor rotation. One pulse corresponds to one step angle. They are active on the rising edge, at the high level of 45 V, and the low level of 0.5 V. Minimum pulse width greater than 1.5 microseconds. Pins 3/4. Direction signal. They control the rotation direction. They must be set at least 5 microseconds before the pulse signal. Pins 5/6. Enable signal. They control the driver's start/stop, enabling it at high level and disabling it at low level. They can be left unconnected, and the driver defaults to enabled. 2. Interface P2, power and motor wiring. Pins 1/2. Power supply input. Recommended, plus 36 VDC. Operating range, plus 20 V to plus 50 V. Pin 1. GND pin 2, V+. Pins 3/4. A+/A- phase wires. Pins 5/6. B+/B- phase wires. These connect to the two windings of the stepper motor. Number 3. Wiring specifications for stepper driver modules. The M542 stepper driver supports differential signals as well as common cathode and common anode single-ended signals, offering strong anti-interference performance. It is ideal for long-distance transmission and complex industrial environments. Interface wiring circuit examples. Figure 1. Open collector output, common anode. Figure 2. PNP output, common cathode. Anti-interference wiring recommendations. Use shielded twisted pair wires. Connect the shield layer to ground. If no true ground is available, it may remain floating. Maintain at least 10 cm distance between control signal lines and motor power lines to reduce electromagnetic interference. Number 4. Requirements for safe operation and hardware protection. To ensure safe operation of the equipment and extend its service life, observe the following precautions. Do not hot plug the interface P2. Doing so may burn out the driver. After completing the wiring, double check that all connections are firm and the polarity is correct. Before powering on, use a multimeter to measure voltages at each terminal to avoid short circuits or reverse polarity. Number 5. Current and microstepping setting, DIT switch description. The M542 stepper driver uses an 8-position DIT switch to configure operating current, idle current ratio, and microstepping resolution. 1. Current setting, SW1, SW3. It is to set the motor's operating current. For example, set the average current to 1.7 A. SW1 equals off, SW2 equals off, SW3 equals on. Select the correct current level according to the driver's current table, so as to avoid underdriving or overloading the motor. 2. Idle current setting, SW4. SW4 equals off. Idle current equals 60% of operating current. Recommended for it reduces heat. SW4 equals on. Idle current equals operating current. For rapid response applications. 3. Microstepping setting, SW5, SW8. It controls the microstepping resolution, i.e. how many pulses are needed for one full revolution. For example, to set 40 microsteps per step, SW5 equals on, SW6 equals on, SW7 equals off, SW8 equals off. A 1.8 degrees stepper motor, 200 steps per revolution, becomes 8,000 steps per revolution after setting, significantly improving displacement accuracy. Number 6. Motor wiring method and precautions. Different types of stepper motors support 4-wire, 6-wire, or 8-wire configurations. In this case, a 4-wire motor is used, connected to the P2 port via terminals A+/A- and B+/B-. Wiring precautions. Avoid incorrect phase sequence, which may cause motor reversal or vibration. Ensure firm and reliable connections. Loose terminals may cause step loss or trigger driver alarms. After wiring, it is recommended to perform a no-load motor test to verify the rotation direction matches the control logic. Number 7. Calculation of the pulse count of stepper motor. In a control system, the pulse count output from the PLC determines the displacement accuracy of the stepper motor. The common formula is as follows. Where P1. Pulse count output by the PLC. P2. Microsteps per revolution, set by the stepper driver. Or 2. Rotation angle of the driven mechanism. Or 1. Rotation angle of the motor. It is also necessary to consider the sprocket transmission ratio, I1 e.g. 19:49, and the gear reduction ratio, I2 e.g. 1:30. For example, assume the stepper motor is set to 40 microsteps per step, and the motor has a step angle of 1.8 degrees, i.e., 200 steps per revolution. To rotate the motor shaft by 1/4 of a full revolution, 8,000 times 90 over 360 equals 2,000 pulses. Therefore, the PLC must output 2,000 pulses to rotate the motor by 90 degrees. Number 8. Demonstration of practical wiring and DIP switch operation. Let's look at a practical operation demonstration. P1 wiring. Connect pin 1 to Q0.3, pin 2 to 0V. P2 wiring. Sequentially connect the ground wire, 24V power supply, A+, A+, B-, and B+. Dip switch settings. SW1, SW2 equals off. SW3 equals on. Operating current equals 1.7 A. SW4 equals off. SW5, SW6 equals on. SW7, SW8 equals off. Microstepping setting, 40x. Motor response test. Check whether the rotation direction matches the expected result and whether the motor runs smoothly. Number 9. Summary. In this lesson, we covered the types and working principle of stepper motors, as well as the signal and power interface layout of stepper drivers. We learned about dip switch setting, current control, microstepping adjustment, motor wiring, and pulse count calculation of stepper drivers, and deepened our understanding through hands-on demonstrations. I hope you can operate personally during the practical training and master the methods of pulse signal control and parameter tuning. Lastly, please complete the exercises after class. That's all for this lesson. See you in the next class.